Hello, welcome back to Math with Patrick. It's June 9th, and we're solving problem number 160 from the Daily Epsilon calendar. Let's figure it out. We need to find the 10th digit of this kind of weird number. It's 17 plus the square root of 280, then raised to the 17th power. So this number seems to be really big. Like this seems to be like a two-digit number, and then raising that to the 17th power will be a fairly large one. So hopefully I won't actually need to figure out what the number is exactly. There hopefully is going to be a good strategy to just target that 10th digit or the 10th place. I think what's going to probably work for me, maybe not, but what's probably going to work is I could get like a decimal approximation of this number and kind of see what happens. So that's my first guess. I'm not sure if it's going to work precisely, but we'll see what happens. I want to know about what this number is. And to approximate square roots, there's the Babylonian method, which we could use. It starts out with a good guess, just a general good guess. I know that 16 squared is 256. And so likewise, the square root of 256 is 16. And 256 is close enough to 280, where this is going to be my first initial good guess. Like, sure, it could be a bit bigger, but oh well. So the process goes, here's your good guess. I'll say X naught, as in like NAUGHT, like not for nothing or zero. My first guess, X naught, is going to be 16. And to create your second guess, you are just going to find the average of your original guess and then the target number divided by your guess. And so adding them together, dividing by 2, is going to create that average. Now, this isn't something that I'm really keen on doing by hand. So I'm just pulling out a calculator. I'm doing the average right now. And the next guess in this iterative process is going to be 16.75. And so we can do that again. And you just kind of keep going until you have your desired accuracy. So let's just see what happens when I do this second iteration. I'm going to plug in this 16.75 in the spot where the 16 once was. And I will find the average of these two numbers. And let's see what happens when I just kind of plug this into my calculator. I'm going to get, a long decimal number. It's not actually equal to this number. Let me use little squiggly lines. It's going to be about 16.7332, and then there's some other decimal places over here. And then if you want, you could also, like I'm using a calculator right now, so might as well just take the square root of 280 anyways. And it's actually pretty darn close. So this approximation method basically got the square root approximation to 5 decimal places, because there was actually a 0 here before I started doing all those dots. So if we want to get a good estimate of what 17 plus root 280 is, we can just add 17 to 16, and then we're going to get 33.7332. Okay. So this is an approximation of the number that I'll need to raise to the power of 17. And now I'm thinking maybe this whole decimal approximation wasn't a good idea, because after enough multiplications, my estimate is going to be further and further diverging from the actual value. So even though now I have a good sense of roughly how big the number is, and it's accurate to 5 decimal places, I don't think that's going to be enough. Just to kind of prove my point, so these two numbers are really close to each other. They're accurate to 5 decimal places. And then let's just see what happens when I raise it to some exponent. And then they're probably going to start diverging in value pretty quickly. I don't want to go all the way up to 17. I don't want to spoil the answer for myself. But I at least want to show, okay, so currently their value is very similar. When I square it, they're still accurate to 2 decimal places, maybe 3 if you round. When I cube it, all of a sudden, now they're off. Like the whole number part isn't even the same. And so by the third exponent, my decimals are at least the 10th place is no longer accurate. And so if we do to the power 4, 5, 6, 7, like these numbers are not going to be the same at all after 17 successive multiplications. The next thing I considered was the binomial theorem. That's a strategy or a formula you can use to expand expressions like this. Like we have a binomial, it's two things being added to each other, and then we're raising it to a pretty obnoxious power. 17 is a kind of high exponent, honestly. Like usually they kind of stop at like 3 or 4 when you're kind of doing binomial theorem stuff by hand. So all the binomial theorem would do for me, though, is offer me a way to expand this. And essentially, doing all those computations, you would eventually result into something that looks like this. The binomial theorem would split our product, 17 things being multiplied to each other, into a sum of a whole bunch of things being added to each other. And there's going to be a whole number component, at least out of this one, where we're going to get a whole bunch of whole numbers added up. Fortunately, those whole numbers don't have a tenths place, and so we could basically ignore all of those whole number parts. And if we're investigating the tenths place of our number, we only need this part. But it's not that simple. We have an obnoxiously big number here and another number with infinite decimal places being multiplied together, and we're supposed to find the tenths place after this. I haven't been able to find a good, concise strategy besides just asking a more advanced calculator and counting out the digits. So we can see here that Wolfram Alpha can calculate a whole bunch of digits, and it's just going to be, an infinite amount because the square root of 70 is an irrational number. So this is our number, and if we just kind of count back enough places and kind of investigate the scientific notation, we will find our tenths digit. And so reading this, it basically says multiply this number up here by 25 tens. And so the first multiplication will bring our decimal point right behind the 7. And then the second multiplication will bring it here. So this is 2 tens in. So then 3, 4, 5 tens will bring us here. And I'll count by my 5s. So once we do 10 to the 10, our decimal point will be moved here. 15, 20, and then by the time we multiply 25 tens into this number, our decimal place will be right where my cursor is, and right after it is a 9, and there's actually a whole bunch of 9s, which is kind of interesting, that there's 9 of them. There's 9 9s after the decimal place here, and it's just that first one, which is the digit 9 that we're solving for in this problem, and I'm honestly befuddled. I have no good solution besides just asking an advanced online calculator that can calculate many digits and just counting it out. This 9 right here is our answer that's matching today's date. And honestly, that's it. It's kind of unsatisfying. If you have a better solution for me, please let me know. I'd love to hear it. But this is all I got. So there's a 9. It's June 9th. I'll see you tomorrow. Bye.